So I don't have the answer of how we do that, but I'm going to try to show you some of the evolution of the methodology that has been happening over the last few years, and then we'll have some open questions that we can discuss afterwards. So the starting point is essentially what Mark already mentioned, that deep learning has already had a huge impact in astrophysics. This is the number of papers using deep learning CNNs as a function of time. And you can see that you have had an explosion of those papers. And there's a very good reason for that, is because the data is very complicated. We want to solve complex tasks on the data, and deep learning is a very good solution for that. But something that Mark also alluded to is that almost all of these works have been based on supervised learning. And so by supervised, I mean that all of these neural networks typically have been trained once to solve a very specific task on very specific data. And that has intrinsic limitations on the applicability and the ease of use of these techniques for doing exploratory science. So I'll just show you a few examples of these limitations of the traditional way that we've been doing deep learning so far. So the first one is that in many cases, we only have very few actual objects in the data that we can use to train these models. So one of these examples is if I'm looking for very rare events on the sky, so for instance, strong gravitational lenses that you see here, we only know a few thousands of those in the real universe. So that's not enough to train a very effective large-scale model to find these things. The other example, which will relate to some of the things we've heard yesterday, is that we know now how to infer physical parameters from data using methods like simulation-based inference or approximate ABC. But this most of the time relies on having access to simulations and then training a neural network on these simulations. And so one of the issues that you run into in these kind of things is that you need to retrain these neural networks that look at the data, extract features every time for every problem. And that means that you need to have access to high quality simulation, and those can be very costly. So that has been what we've been doing so far, but at the same time, there has been this emergence of this new paradigm called foundation models. This is a paper from people here in Stanford, where the approach has changed dramatically. Instead of trying to train a neural network to solve one specific task, the goal of a foundation model is to essentially split the problem in two parts. The first part is going to be this pre-training part, where we are not going to assume that we have access to labels. We're just going to assume that we have access to a large amount of data without particular tasks that you're trying to solve on it or any particular labels. And then from that vast amount of data, we're going to train a model. And then we'll see that there is easy ways of adapting this model to solve a particular task of interest. So that's the big transition from the previous state of deep learning to this new approach, is that now this foundation model can be reused for many different tasks. And what we'll see just after is that in addition to that, some of the emergent understanding of the data that we'll see in the foundation model can start to be interesting for us to try to do some science. And the last point that I want to make here on the left, this is exactly why these foundation models have become mainstream, is that because you don't have access, you don't need to have access to labels, you can train on a lot more data, and by doing so, you can actually reach better accuracy in many cases. So this is illustrated on the left, where on the y-axis you have a classification accuracy on an image classification problem. The models that you have on the left, these are supervised models. You can see they can only reach a given size because they are limited intrinsically by the amount of labeled data that you can use to train them. And then on the right, these are unsupervised models that you can train on much more data and then adapt to this particular task, and you can then reach larger models and better accuracy. So that's kind of the idea. And then the last point that I want to make, there are different sorts of foundation models, but the things that we are going to talk about today is mostly going to be about representation learning and then easy adaptation of the representation that you've learned for solving new tasks. So let's start by the plot that you see on the left. When I have these base models, there are different ways that I can adapt them to a new problem. If I'm talking to ChatGPT, you could, for instance, prompt it by changing the text that you have an input, and then you will transform it into a model that can solve a new task. But what we're going to look at is this middle thing here, linear probing, where we're going to assume that we can extract essentially vector embeddings from the different models that we're going to talk about. The details don't matter too much. But then from those embeddings, will be able to learn a mapping that you can see with this M matrix that you see here at the bottom to turn these embeddings that are very general into predictors for whatever property that you're interested in. And what you see here on the right is just to showcase that if you use this approach, so you have this large foundation model, you have just a projection on top of the representation as learned, with very few examples of the order of 10 examples per class in an image classification problem, you can turn that self-supervised model into a predictor for image classes, and you will saturate the performance. So you can, the bottom line is that you can do whatever task you want, you reach state-of-the-art performance by just a very simple adaptation of a frozen existing model. And that in itself is going to be very powerful for us. So why? For several reasons. The first one is that if I am an astronomer and I want to do deep learning, I will never have to retrain my old neural network. I can directly use an existing off-the-shelf network, and that's going to save me a lot of time. The second point is that because now the thing you need to train in order to adapt to a new task is just this little layer that you plug on top of it, you can train that layer with very few samples. And so you can effectively do deep learning, very powerful deep learning with very few examples. And so, for instance, this is great for finding rare things like gravitational lenses. And the last point is that the tools that you need in order to turn this foundation model into whatever you want are extremely simple. So in what I showed you, linear probing layer, this is just a linear regression on top of the foundation model. So the point is that you can become state-of-the-art deep learning scientist with scikit-learn, and that really changes the ease of use of these tools and how many things you can do with them. All right, so that's essentially the context and the reason why we're interested in this. And now I'm going to show you a few examples that have appeared as a function of time of this idea. And the first one, I think, is this paper from 2021 from a group in Berkeley, where they build such a representation learning model using this idea of contrastive learning. So the idea here is that you take images, you will create augmentation of those images, so you perturb them in some way, and then you will feed them to an encoder. So that encoder is going to take the image and output a representation. And the training task here that you're trying to solve is that for two images that are augmentation of the same input image, you want the embeddings, so those vectors, to align very well with each other. But if I show it two images that are actually not associated with each other, they should be very misaligned. So it's just a simple strategy to build a vector. And what they were already showing at the time is that if I pre-train with this strategy, then I can get those vector embeddings. And by very simple adaptation on top of those vector embeddings, I can solve a whole bunch of tasks. So finding similar objects, classifying galaxy morphologies, for instance, predicting physical properties such as redshift or stellar mass. And so that was one of the first illustration of the fact that you can now have those very general models that you can adapt to many tasks. At the time, I don't think it was really realized how powerful this would ultimately be, but these people did it at scale. And then the next point that I want to mention is that, and we'll talk a little bit more about this after, is that if you start to look at the structure that you have in this embedding space, it's not random. It has some information. So this is a UMAP visualization, if I'm not wrong, of the space that has been discovered by such a model from Galaxies from HSC. And if you look at local neighborhood in this representation, you see that they look very similar. And more than very similar, these galaxies, they will also share very similar physical properties. And so you have a notion of similarity both in the way that they look like and in their physics. And that you can also use to then find very interesting examples of very rare objects that you might be interested in. So this is in a paper finding galaxies that have low surface brightness features that might be tracers of recent merger events. And by just showing one example of this object that you're looking for, so the one that you see on the left, you can find a ton of very similar objects. And so you can discover very easily objects you can do science with. All right. So that was the first generation, let's say. So trying to go from building representation from the data itself without labels. Now there has been, in the last couple of years, a lot of excitement towards being able to build representation across modalities. So as Mark said, we are interested in bringing together data from different instruments, but also different types of data. So the starting point for the discussion is going to be this paper from OpenAI from a few years ago, a method that they call CLIP, which is very simple. The idea is that you're going to try to train those encoders that build those representations by having two modalities. Here it's text and images. And you're going to train this system such that when I show an image that corresponds to the particular caption, the embeddings, again, should be well aligned. And when the text does not correspond to the image, I should minimize the alignment between the embeddings. So this is no longer completely self-supervised. You would sometimes call it weakly supervised pre-training. But it has the effect of creating also a very powerful representation space that is consistent between text and images in this case. So in a paper for last year in my group, we deployed this exact idea, but instead of text and images, we went for real data in astrophysics. And we applied this idea by using spectra that tell you essentially a lot of information about the physics of the objects on one hand, and galaxy images on the other from different instruments, right, different telescopes. And the interesting thing that emerges from doing this is that you discover a space that is consistent between imaging and spectroscopic information, and that has a lot of nice properties that align very well with the underlying physics of these objects. So one way to show that there is consistency in the space that you've discovered is that, for instance, if I want to predict a physical property of an object, I can build a really powerful estimator by just taking the embedding of an image, looking for the spectrum that is the closest in that space to that image, and then assigning the physical properties that correspond to the spectrum, which I can know by doing some physical analysis on it, and using the nearest neighbor essentially as a predictor for the physical property I care about. And if you play that game, you can find that it will outperform any other supervised benchmark or baseline that you would have in this case. So I'm not going to go over all the details, just to say, I'll just highlight the thing that you have here on the left, that it's an example of how easy it is to build a new predictor for a new problem, given these foundation models. In 3 lines of code, essentially, you can estimate, I don't know, stellar mass or redshift very easily, and you will beat the state-of-the-art of supervised methods on this. All right. So I'm not sure. All right, okay. So that was some of the first work. I'll just highlight very quickly this work that Mark and his team led in Euclid, where the idea this time was not using contrastive learning, but essentially generative pre-training. So building a decoder-only transformer that you train to understand both galaxies and SCDs, galaxy images and SCDs, and then you can try to inspect the space that has been learned by this model, and you will discover, again, a lot of structure that aligns very well with the physical properties of the objects, to the point that if you try to do, for instance, from that representation, predict something like the stellar mass of galaxies, it will outperform the baseline that are otherwise in the pipeline. So these things are completely, data-driven, but they will outperform your physical model. All right, and I'm going to finish on trying to go beyond. So here I've just shown you examples of bringing 2 modalities together. But as Mark said, in principle, we would want to go into the world where we can bring all the data into one model and then maybe understand something about the physics of these objects there. So there is a first hurdle that you have to overcome, is that data lives in many different places depending on which instrument it comes from. And that's a project that we did last year where we try to gather a lot of that data in a single format as Hugging Face data sets that you can then very easily use for training models. And more interestingly, for a given object on the sky, I can easily extract any modalities that relate to that object, any measurement that relate to that object. So once that I have that, this is a project that we've just finished. I can build a data set that not only includes images of spectra, but images from different instruments, spectra from different instruments, whether it comes from the ground, from space. And I can try to build a model that can ingest all of these data by first going through a layer of tokenization. So I build these encoder-decoder systems that can take any type of data, whether it's images or spectra, turn them into tokens in the same way that you would see in a language model. And then I can build a large transformer model that can learn from a mixture of these tokens to predict missing tokens. So I won't go into all the details, but the main point that I want to highlight here is that at this point, you're building a generative model that you can use to generate any data conditioned on any other data, or even without conditions. And just, well, let's see if this works. Oh, well, it doesn't, so. Okay. Just to show you what these models can do, they can, for instance, be used as generative models. Here, I condition the model on some input data, whether it's here it's on spectra, on images in the middle, or on images on the left. And I can ask for generating any other modalities. So this is not necessarily the perfect solution yet, but it's showing you that in the future, we'll be able to build the generative models that can replicate all the data that you see on the sky. And I'll just maybe highlight here this example on the right, where we condition at the input a low-resolution spectrum that comes from the Gaia satellite, and we ask the model to generate a high-resolution spectrum for the star. And you can see that these dips that you see here, they are not seen in the input data, but the model understands the physics well enough that it knows that it should put it at the input on a high-resolution outputs. And I'm just going to conclude with this. I'm going to skip it. Just the last sentence. We've seen that these models start to understand our data across all of the different ways that we observe these objects. But then the real question that's going to be interesting for us is, can we learn something from these embeddings, from the space that has been discovered? And that is still very much an open question, but I'll show you some hints of interesting features. What I show you here is the result of doing one of those contrastive learning tasks by using this sort of augmentation on the data to create pairs of images. And the middle row is the comparison of the embedding space that you discovered, colored by different properties of the objects that you're looking at. On the left, using a traditional PCA analysis, and on the right, using this contrastive learning method. The interesting thing is that here we're plotting two types of parameters, one that is physical, that really has to do with the underlying object, and on the right, these instrumental, these have only to do with the details of the observations. And you can see that in the traditional approach, this space, the structure of that space is actually very much driven by the instrumental details. And the instrumental details here are far less impacting the representation that you've learned on the right. So the point is that we're going to move towards a space where you can disentangle better the different aspects of the physics you're looking at and potentially identify the key fundamental physical properties of the objects you're looking for. I'm going to skip this, and then I'm going to move to David.